Hi, hello. Today I am going to explain about bumping lemma for regular expression. So here first I have to explain about the definition. If L is a regular language represented with an automata with a maximum of n states, then there is a word in L such that the length we here we can represent it as mod z. So modulus z greater than or equal to n. Further, we may write z equal to uvw in such a way that modulus of uv less than or equal to n and the length of v it is greater than or equal to 1, and for all I greater than or equal to 0 u v to the power I w is in L. So here in this definition, if L is a regular language in an automata, so here we have to mention the number of state. The maximum number of n states are there. So in a language, it is possible to write many strings. Here the word is nothing but the strings. So then there is a word in L, a string in L. So the length of the string is greater than or equal to the number of states. For example, L equals AB means or Z equal to AB. So this is the word. Here the number of states is 3 and the length of Z is always greater than n here. So here the length of Z is 4 and length of n is 3. The total number of states is 3 here and the length of Z is 4 here. So it is greater than n here. So further we may write, so how we can write the word means UVW. We can write this part into UVW. So in UVW, the length of UV is less than or equal to number of states. This is the first condition. So here the length of UV is less than or equal to number of states. Number of states is 3 here. So the length of UV it is less than or equal to 3. And one more condition, length of V. Again in V, definitely it should not be a epsilon. So it should contain at least the length of V is 1. At least one character in the word or string it is mandatory. And for all I here I it is the loop in this language, that is UVW. Here in the string we can write this as UVW. In the V part the loop is there, V to the power I. This I value is always greater than or equal to 0. So if all the conditions are satisfied, then UVW is in the language. So as I already explained the definition, so here the number of states is 3 and the input is the string is AB. So here I am taking the NFA diagram. Suppose if you are taking DFA means for each and every state the input is only 1. But here the number of A's in state 1 is 2, from 1 to 2 as well as 1 to 1 loop is there. So it is the NFA diagram. So any number of A and B is starting, that is in the initial state, it may be start with either A or B or any number of A's or any number of B's, because here it is the loop. But definitely it should end with AB. That is the language here. So here there is one example for this pumping lemma. So here the language we are taking is L equal to A to the power n, B to the power n, and the n value is greater than or equal to 1. So we have to prove it is not a regular. So if you want to prove it is not a regular means, first here we are going to prove it by contradiction. So first we are assuming the given step L is a regular language. That is the first step. We are going to prove it is a not regular. By contradiction method, we are going to prove it is a not regular. So the given language L is regular here. We are assuming like that. In the second step, if L is regular, then for above this condition we have to check. We have to take the word, we have to split the word into 3 parts UVW. Here we are taking, instead of UVW, here we are taking it as XYZ. and the length of xy is, or the w is greater than or equal to n. That is the total number of the characters in the word, that is in the string. It is greater than or equal to number of states. Here we can take it as that. So z is greater than or equal to n in the definition. Here I am taking it as w. So the condition is same. And the length of y, it is greater than or equal to 1. It should not be a epsilon. Then we have to check whether x y to the power I z it's belong to the language or not. So from the given language we know any number of a's, that is n number of a's, that is followed by n number of b's. So here some number of a's are there and some number of b's are there, followed by some number of b's. So w equal to, this is our input. Now we are taking this as input. So here we have to split this input into three parts, x, y, z. So in x, y, z it may be in many combination. So for in the first case we are taking xy as a. So up to this a we can split it as xy, and b part we can take it as z. So here the length of x, now we have to know about the length of x as well as length of y and length of z. So we know here there are n number of a's. So x equal to a to the power n minus s. Here the length of y is a to the power s. Suppose if we are adding these two parts, then that is concatenating these two x and y means, then we can get the a value, number of a is a to the power n. Suppose if you are adding means the base are equal here, so a to the power n minus s plus s, we are cancelling minuses and pluses. Finally we can get a to the power n. So we can split the a value like that is x and y value like this: x equal to a to the power n minus s and y equal to a to the power s, and z equal to b to the power n. The total b is considered as b to the power z here. So we know that it is belonging to x to x, y to the power I, z belongs to L, I greater than or equal to 0. We know the length of x. So a n to the power n minus s. This is length of x. So here we can put this value x equal to a n to the power s. And y we know it is a to the power s. So a to the power s, it is in loop, so we can take it take the power I to here, and z is b to the power n. So total this length of this language, that is the string of this language, is a to the power n and b to the power n after adding these things. Here I is in loop and I value is always greater than or equal to 0. Suppose if we are taking 0 and 1, it is regular. So it is belonging to the language. But we have to satisfy it for all values of I. Suppose if we are assuming I equal to 2 means, so here a to the power n minus s, a to the power s, for I we are substituting the value 2, b to the power n, come as it is. So here for this power s to the power s square means that is a to the power s power 2 means we are multiplying this 2 with s, so to the power a to the power 2s. Here these two a base are equal, so we are adding the power a power n minus s plus 2s and b to the power n. After subtracting this s, here we can get a n plus s concatenating b to the power n. But our given language is a to the power n, b to the power n, that is n number of a's and n number of b's. But here the n value is, a value is greater than n here, so it does not belongs to the language here. So by contradiction method we prove it. Suppose if here it is possible to split the value by any chance. Here we are taking the value of s and y is a value. Suppose in the case 2, if we want to consider all a's as x and we split the b as y z means, similarly it is similar to the previous case, but here Suppose if we solve by using the same method means b value is more than a here. Number of b is greater than a. But by given language, both a and b, it contains the n number of a and b and n number of b. So it is also not belonging to language. In case 3, suppose if we are taking w equals AAA, BBB means, so here we can split the given word into X, Y, Z. So here some number of A's we can consider it as X and some number of B we can consider it as Y. In between AA, BB as Y means, suppose if you are substituting the same in the condition X, Y to the power I, Z belongs to L. So here we are taking X value as any number of A's here. Y value we know it is AABB. I value is 2 means we can repeat the Y value by 2 times. AABB again AABB and any number of B's for Z here. But contradiction occurs here because from the given language a to the power n number of a's followed by n number of b's, but here in between bb is also occur. So it is contradiction occurs here. It does not belongs to the given language. So here by we are proving the given a to the power given language a to the power n b to the power n, it is not a regular language. Thank you.